Hi, I'm Tudor Davies.
And I'm James Dury.
And we're from Spectrum Signal Processing. Today we'd like to show you our XMC 1151 high-speed digitizer card with Vertex 6 FPGA that's user programmable on it. The card is available with high-speed digitizing ADC with 2 channels at up to 1.8 gigasamples per second, or single channel at up to 3.6 gigasamples per second, and that's at 12 bits. The card is also available with 3 different sizes of FPGAs, which are user programmable. You can use the Vertex 6 LX240T, the Vertex 6 SX315T, or the Vertex 6 SX475T. So the SX is a signal processing optimized, lots of multipliers, and the 475T, the amount of logic. So quite a large FPGA, lots of space. So in the system for this demo, what we've got is we've got a 2-channel signal generator. Each of the 2 channels is connected through a filter. We want the signal from the signal generator isn't as clean as what you can get on the digitizer. So we want to have as clean a signal as possible. We want these filters to remove the spurs from this signal generator. So we're going to go through these cavity filters. This one is a tunable filter. This one's just a smaller one. It's fixed frequency at 490 megahertz. We can take signals up to 3 gigahertz into the digitizer in either 2-channel or single-channel mode. So even if you're only sampling at 1.6 gigasamples, you can put in a signal at 3 gigahertz. You can see it just fine. Now, run the signals from the filters through these cables into the 2-channel inputs of the XMC 1151. In this case, the XMC 1151 is mounted on a carrier inside the PC, and the PC is running Linux, and it's an Intel i7 processor in there. You can also mount the XMC 1151 on different types of carriers. We have carriers available for, obviously, PC, for VPX, and also you can get an AMC carrier, and you can mount it on different types of carrier boards such as 6U, XMCs. As long as it has an XMC site with PCI Express, you can use this card in that environment. And you can mount it on an XMC carrier board. So the XMC module, these connectors mount to these connectors here. And so this carrier board happens to be a PCI Express carrier board, so I can mount it onto here, and then this carrier board just goes into a PC. You can see the PCI Express connectors here. It's got a cooling fan that blows air over the XMC module. So that's one way to mount it. You put the same module, so you run this in a PC, you run Linux on it, do your development, and then you can take the same module out of the PC environment and you mount it on a 3U VPX carrier board. Be careful to make the connectors correctly. Mount that on here. And now I have the same thing in 3U VPX. If I have a single board computer that is also running the same operating system, Intel i7, I can port from the PC to the Linux environment in OpenVPX with no changes to my software.
This is the XMC 1151. It's mounted on a PCI Express carrier board. These are the 2 signal inputs, a reference clock input, a 1 PPS input for triggering, an external sample clock input, and sync in and sync out, which are used for multi-board synchronization for phase coherent sampling.
Okay, so we're in the Linux computer, and we've got the terminal window open, and this is running Red Hat Linux 5.9. So we're going to run MATLAB. And with the ampersand to keep it open, keep the terminal window open. So MATLAB is coming up, and then once we're in MATLAB, we're going to run this GUI, the ADC capture GUI. So we'll start that. We've got this nice little GUI here, which lets us play with the ADC. We have a number of options in here. One of the features in this new version of the XMC 1151 is that we have a instead of having a fixed sample clock in the internal clock, we have a variable sample clock. It's using a programmable clock synthesizer. It has a couple of advantages. One of them is it's got a very clean clock, and the second one is that we have this slider where we can actually change the frequency, the sampling frequency. So we're going to start at the default of 1600 megahertz. And one of the things that's always a good idea, we have a calibration routine. So these very high-speed ADCs generally require calibration when you first start them. So we're going to do that. That takes about 20 seconds when we first start it. And so we have a number of options here. We can have receiver 0 and receiver 1 selected. We'll start off with one of them. And if you click on double edge mode, that means on the rising edge of the clock, one of the ADC samples, and the falling edge of the clock, the other ADC samples. So effectively, you've got double the sampling rate. So that's what lets us use single channel mode, which they also call double edge mode, at 3.2 gigasamples per second in this version of the board. So first one, we're going to do a single shot. We're going to calibrate it. So we click run. We get the icon saying we're running. And while this is calibrating, it takes about 20 seconds. So we finished calibrating. This was a single shot. And so you can see now this particular input, we've got an input frequency of 2350 megahertz. And we're sampling it at 1.6 gigahertz. So these are actually aliases. So 2350 megahertz is 1600 plus 750. So that's where we see this line here at 750. So because we're actually operating in the third Nyquist zone. So the first Nyquist zone is from 0 to half of Fs. That's at Fs over 2. The second Nyquist zone is from Fs over 2 to Fs. Third Nyquist zone is from Fs to Fs times 1.5, and so on. And so this particular ADC, I've operated it personally well up to 3 gigahertz, even operating at a sample rate of 1600 megahertz, so well into the third Nyquist zone. So actually the fourth Nyquist zone. So we can operate well up there. The analog bandwidth, it's a full power bandwidth to 2700, 2800 megahertz, and you can easily operate it up and a bit above 3 gigahertz. So let's just change the frequency a little bit. So first thing I'm going to do is I'm going to hit continuous mode so that it just keeps on resampling. And I'm going to put both channels in. So I'm going to start sampling both channels. And I'm going to click run. And what it's going to do, you can see the script running in the background. So it's sampling at both. So here I've got two channels. In one channel I've got an 850 megahertz signal. So that's 850 there. But I also see the alias here. Now I've got another one at 2350. Which one's 850? Is that one or that one? This one I've got at 2350, and it looks the same. So I can't tell really whether the signal that I'm looking at is in the first, second, third, or even the fourth Nyquist zone. But what we're going to do on this one, so on channel 0 of 0 and 1, we're going to change the frequency. So right now it's 2350 megahertz. So let's reduce that frequency down to 2200 megahertz and see what happens with this signal here. Now, the noise floor came up because we had to change the filter as well. So now you change the frequency, then you have to change the filter, the signal generator. So now we've got the signal down here. So it's 2200, which is the sample rate of 1600 plus 600 megahertz. So I actually see the signal at 600 megahertz, although it's actually Fs plus 600 megahertz. And I also see another alias here. Now this one, of course, it's a fixed filter, so I can't change the frequency. So that's in single edge mode. So let's just try changing the frequency here again. We'll go from 2200 to, let's say, 2 gigahertz, and we'll see what we get. Noise floor comes up while I'm changing the filter, and so here's my signal at 2 gigahertz, and so I'm sampling that at 1600, 1.6 gigahertz, plus 400 megahertz, so I see the signal at 400 megahertz. Okay, so that's playing with the frequency. Now, the next thing I'm going to do is I'm going to change the sample rate. So, in order to change the sample rate, I have to stop, and then I'm going to change the sample rate. Let's just take it down to 1 gigahertz. So I'm going to sample at 1 gigasample per second. I'll leave the signals the same, and we'll see where these signals move to. So we'll run. Actually, one thing I forgot. When you change the sample rate, it's recommended that you calibrate the ADC again, because the ADC operating at a different sample rate, it gives you best performance if you calibrate it. So we'll run that, and that takes about 20 seconds. So while we're running that, you can see we've got the slider on here to change the frequency. What we've got implemented on here right now, we're using on the slider, we've got 100 megahertz steps, because that gives us the best phase performance in the synthesizer. We can operate the synthesizer in integer mode, which gives us the best phase noise. You can operate that synthesizer in finer resolution, but it gives you better performance when you're operating in integer mode. So we're sampling at 1 gigahertz, and our frequency is, let's see, what's our frequency on the signal generator is 2 gigahertz, so that's probably not a good choice. Exactly twice the sample rate. So let's change the frequency to 1.9 gigahertz, and we'll you don't want to have signals exactly at the sample rate, so we just change the filter. Okay, so now what we've got is the signal is at 1.9 gigahertz. We're sampling that at 1 gigahertz. So the real signal is at 900 megahertz, but we also have an alias here because that's 2fs minus 100 megahertz. So we've got fs plus 100 megahertz, fs plus 900 megahertz, and we also have 2fs minus 100 megahertz. So those are the two aliases that we see here. Okay, remembering that whatever Nyquist zone the signal is, you always display it at in the first Nyquist zone. Second one is this one. So this signal is at 850 megahertz. We're sampling that at 1 gigahertz. So fs minus 150 megahertz, that's our 850 megahertz there. We also see 850 in this side of the window. Okay, so that's single edge mode, which is 2-channel mode. So what we're going to do next is we're going to change the mode. We have to stop it to do that. And we're going to go to double edge mode, and we're going to go to the max clock frequency, which in this case is 3.2 gigasamples per second. And we're going to run that, and again we're going to calibrate it because we've changed the sample rate. It's not mandatory, but it's recommended whenever you change the sample rate. And whenever you power up, you should also calibrate. So we're going to run that. So while we're calibrating, we'll just look at this slider here. This one allows you to change the number of samples. We're capturing a block of data into memory, and we're transferring that to MATLAB. And in the MATLAB, we're running an FFT on it. Okay, so here's our signal. Our signal is at 2 gigahertz. Is that right? No, we're at 1.9 gigahertz. So this is the signal at 1.9 gigahertz, and that's its alias. So obviously when you're in single channel mode, we're not going to see the other channel. That's double edge mode. So let's change the frequency now. Let's go back up to 2.4 gigahertz. And obviously the noise floor comes up while we are changing the filter. So here we are at 2.4 gigahertz, and we've got an alias, of course, there as well. So what we're going to do is we're going to stop this. Oh, but while we're here, let's just change this. We don't have to stop to make this change in the GUI. So we can actually go to the time domain. Now let's just change the slider a bit. So we can actually zoom in on the signal. Zoomed in on this 1.9 gigahertz signal in the time domain. But I think the frequency domain is a bit more interesting. This slider changes the resolution here and the time. So there's our 1.9 gigahertz signal. You can see the noise floor jumping around a bit. But if we stop, we can actually change the number of samples that we use in our FFT. So right now we've got about 262 mega samples or kilosamples. We stop that and we can run the slider up, just using a larger sample size. Now obviously the FFT is going to take longer, so it doesn't update as often, but let's just observe what happens. We can see where the noise floor is now, and when we run it with a higher FFT size, let's just have a look at what it does with that. Obviously it takes a longer period of time to compute the FFT, but now that we've taken the FFT, it obviously is going to update much more slowly, but you can see that the noise floor has gone way down. The spurs are at about the same level, but the noise floor has gone way down because we are gathering a larger amount of data, and so each Fourier bin is smaller. Okay, so we've gone through, just to review, we've changed the sample clock, both in single edge and double edge mode. We've got the running at the maximum sample clock of 3200. It actually is possible to overclock this ADC. We played around with that, but I'm not going to do that today. We've changed the FFT size in order to have some effects on the noise floor. We've seen the operation in different Nyquist zones. By the way, 2400 is as high as my signal generator goes. I can go up above 3 gigahertz and still see the signal, but I don't have a signal generator today that I have available to use that. You can see the double edge mode for single channel up to 3.2 gigasamples, or two channels at up to 1.6 gigasamples, but you can still see signals well up into the third and fourth Nyquist zone. There were a couple things that I forgot to show you before. So just a few of the features on the GUI here. So we use the calibrate button. So this one, wait for 1 PPS signal. That's actually waiting for a trigger signal. We usually use 1 pulse per second, 1 PPS, from a GPS receiver, but this trigger can come from any other source. It's going to a front panel input, a coax input, and it takes a TTL signal. And what that does is when you have this selected, it waits until it receives an external trigger, and then it starts the capture into SDRAM of the sample stream, and that sample stream is then transferred to the PC. So what this does, it allows you to wait for an external signal. For example, let's suppose you want to capture a radar pulse or something like that, and you have an external trigger that can tell you when you want to capture that. That's what that one is for. We use 1 PPS from a GPS receiver because it's useful for synchronizing multiple boards. You have multiple boards, you can use a GPS receiver for an accurate time base. Okay, the comparison clock, that's used for the synthesizer. If you want to use a comparison clock at 10 megahertz, it lets you use an external 10 megahertz reference. Normally we use the 100 megahertz. It gives you a little bit better phase noise. That's what this section is for. The reference clock. So right now we're running on our own internal 100 megahertz reference clock, and that is used to feed the synthesizer that generates the sample clock. In addition, you can use an external reference running at 100 megahertz, or you can use an external reference running at 10 megahertz as at the input. So those feed into the synthesizer. The synthesizer, you can also bypass even the synthesizer to use an external input clock. So you can bypass the synthesizer, use an external input clock. For instance, if you want to synchronize multiple boards to the same ADC sample clock, you would use this. Second option, you can use that's using the internal reference, so external clock in for the sample clock, external reference at 10 or 100 megahertz, or the internal reference clock and the internal sample clock. Okay, so we'll stop that, and we'll show you a little bit more about the board.
Okay, so we're going to do a little bit of a tour of the block diagram of the XMC 1151. Here we have the two analog inputs. They're labeled A and B. They're also called 0 and 1. And they go into the ADC, the analog to digital converter, 12 bits. You can sample at a single channel at 3.6 gigasamples per second, or two channels at 1.8. That's if you have the 12D 1800 installed. Today we have the 3.2 gigasample and the 12D 1600 installed. Two channels at 1.6 gigasamples per second, or one channel at 3.2 gigasamples per second. And if you're sampling on a single channel, it samples from channel 0 or channel A. In addition, we have the synchronization connectors, sync in and sync out. These are specific to this particular type of ADC, and it's to synchronize multiple boards. One is coming in from the master, and this one's a slave. It goes out to the next one down the chain. So you can daisy chain these, and it's to synchronize the parallel multi-sampling transfers to go to the FPGA. In addition, we have the programmable clock synthesizer. This is a new feature in the latest revision of the XMC 1151. So instead of having a fixed frequency oscillator, we have a programmable clock synthesizer, so you can change the sampling frequency of the 1151 of the ADC by programming this. It runs on either an internal reference, which is a 100 megahertz reference, or it can run on an external reference, nominally 10 megahertz, that's the most common, but you can also use an external 100 megahertz reference. You can also bypass the system and use an external sample clock. So if you want to synchronize multiple boards in, say, a beamforming network, you want to use the external sample clock. It gives you the best coherency between channels. And then we have it's labeled as 1 PPS or iRig-B, but you can also use it as a trigger input. It's just an input directly to the FPGA from a front panel coax connector. So we can use that as a trigger for things like, first of all, the most important is for synchronizing multiple boards. So you have three things. You have the synchronization for the ADCs themselves, you have the external sample clock, and you have a trigger to synchronize the FPGA so they can line up their FIFOs so that you know which sample on each FPGA is sample number 1. You can line those up in time. So that's the analog front end. And then we have the user programmable FPGA. It has a number of interfaces which we call the wrapper. It provides the ability to program your own application inside the FPGA, but we provide interfaces to the external devices, and this is a modular structure that we call the wrapper. So the FPGA can be a number of different sizes. The LX240T, it's a Vertex 6 FPGA. The SX315T, the SX series has more signal processing elements, particularly multipliers. And then the largest one is the SX475T, and that's the one that we have installed in this demo today. Each FPGA also has 2 banks of SDRAM. It's DDR3 SDRAM at 512 megabytes. It has a 32-bit interface and on each one, so you can use those in parallel. The host interface is a PCI Express Gen 2 X8, so 8 lanes. that has a capacity of up to 4 gigabytes per second in each direction at the same time. In addition, we have the secondary XMC connector. It has a number of differential high-speed serial connections, and it also has GPIO. So this can be used for some high-speed serial protocols such as Xilinx Aurora, Serial Rapid I/O, or PCI Express. It also has a number of general-purpose I/O pins available to the secondary XMC connector. So that's the block diagram of the board itself. Now let's have a look at the system that we're operating today. So on the left we have the XMC 1151, which is the board. That one is mounted on the PCI Express carrier in the PC, and on the right we show the actual PC system. So we have the two receiver inputs. We're not showing all the other connections on this diagram, and we're just going to trace through the path of data as we're passing it through in the demo today. So we're capturing the samples into the FPGA, and we have some software which is part of the examples that we provide that you can use to develop your own applications. In the examples we have a capture program which just captures the raw incoming samples in a snapshot to the DDR3 SDRAM. So from there we transfer that to the PC, and we'll just talk a little bit about the software and how we're actually doing that transfer. On the PC we have the MATLAB based GUI, so we actually have MATLAB running under Linux on the i7 processor on the Linux PC, and that it basically has a control path, and what it does is actually calls an executable program, and that executable program exercises control over the PCIe bus to the XMC 1151, and it selects, it controls the capture, and it also gathers the samples. So it captures the samples, and the samples actually follow a path, and it's used using a structure called a Linux pipe, and that is then piped into the MATLAB GUI. In the MATLAB GUI, we just perform an FFT, fast Fourier transform, and then we display the spectrum. And you'll see the spectrum on the actual GUI as we go.